Hello and welcome back to another video lesson in Math 1106, Business Precalculus. I'm John Adamski, and last time we talked about exponents. This time I want to take multiple terms and talk about different operations, not exponents, but how to multiply, add, and subtract algebraic expressions, starting with rational numbers before we move on to more complicated things with variables. We'll talk about combining similar terms. I'll throw in some rational coefficients and some terms with radicals to make it a little bit trickier. And then we'll talk about how multiplication and addition interact with each other with the distributive property. And lastly, we'll finish with just some special products that you could figure out for your own, special product formulas that you probably want to memorize. You could figure them out as you go, but they could pop up so often that we'll just pay special attention to those at the end, okay? All right, let's use this first example to go over how I multiply, add, and subtract rational numbers. Rational numbers, that means the root ratio refers to a fraction. So these are numbers that can be written as fractions. Okay? How do I multiply fractions together? Well, that's actually the easiest operation to do with fractions. I multiply the tops together. 3 times 6 gives me 18. And I multiply the bottoms together. 7 times 5 gives me 35. That's my final answer. That's very easy. Now, let's look at part B. It's also asking me to multiply fractions together, and I could do it the same way. I could do 8 times 45 over 9 times 28, but the numbers are going to get very large, and they actually don't have to get that way. So if I think about what's going on here, there are some common, well, I'll write it this way. 8 times 45 over 9 times 28. I see one way to get my answer, but the numbers are going to get very large. Now, we know that when the same factor appears upstairs and downstairs, they can cancel. Okay? So let's see. That 9, there's a 9 downstairs, and 45 is a multiple of 9. Also, 8 and 28 are both multiples of 4. So let me take that 8 and write it as a 4 times 2. And let me take that 45 and write it as a 9 times 5. Okay? Then I've got 9 times 4 times 7 downstairs. By exposing some of the factors of the terms that I see some common factors in both the top and the bottom. Okay? I see that there's a 4 here and a 4 here. Those can cancel. I'm dividing the top and the bottom of this fraction both by 4, which is perfectly fine. This 9 and this 9 can also be canceled out, okay? And I think that's all the cancellations that I see. So I'm left with 2 times 5 is 10 divided by 7. And that's my answer. It's simplified, it's reduced, and the numbers never needed to get that large, okay? If you're looking for a review of this, if you're feeling a little lost here, the term you would want to Google would be cross-cancel. Okay, that's where I'm canceling some factors of 8 with some factors of 28. I'm canceling some factors of 45 with some factors of 9. Okay? Now in part C, I'm not multiplying fractions, I'm adding fractions or subtracting fractions as well. That's easy to do, but you need common denominators first. So if I look at what these denominators of 8, 6, and 12 are, what I need to compute is their least common denominator. Okay, the LCD, the least common denominator, which is the least common multiple of those numbers. Okay, so if I look at multiples of 8, you got 8, 16, 24, you can keep going. If I look at the multiples of 6, you've got 6, 12, 18, 24. I could keep going. And if you look at the multiples of 12, you've got 12, 24, 36. I could keep going. And my least common multiple, okay, is the smallest number that appears in all of these columns, and that's 24. That's the smallest number that's in all 3 of those columns. It's the smallest number that's a multiple of 8, 6, and 12. Why is that important? Well, it means that this first fraction can be written with a denominator of 24. To make the denominator 24, that 8 needs to get multiplied by 3. But I can't just multiply the bottom by 3. I have to also multiply the top by 3. multiplying by 3 over 3 is harmless because that's the fraction 1. 3/8 times 1 is still 3/8, though I can see that it's going to now be written as 9 over 24. Going on to the second term, I've got a minus 1 over 6th, minus 1 over 6th. I want that denominator to also be 24. I can do that by multiplying the 6 by 4. That would give me 24. I need to do the same thing upstairs. Now I've got a minus 1 times 4 is 4, divided by 6 times 4 is 24. See, I've got the same denominator. And lastly, I've got a plus 5/12, and I want to turn that denominator into 24 also, which means I need to double that denominator. As long as I double the numerator, that's fine. This is still the fraction 1. That's not going to change the value of this fraction, but it's going to look different. Now it's 10 divided by 24. Okay? Now that we've got common denominators, or the denominator comes from denomination. It's just the name for the thing that we have. We have 9 24ths minus 4 24ths plus 10 24ths. So in the end, how many 24ths do I have? Well, 9 minus 4 would be 5, and 5 plus 10 would be 15. So I guess I have 15 24ths. And these are both multiples of 3. That's 3 times 5 divided by 3 times 8. And when you cancel these common factors, you're left with 5/8. My final answer. All right, let's take a look at this example. I've got a polynomial, and from which I'm subtracting another polynomial. Okay? Now, these parentheses here are important because this polynomial has 3 terms. By the way, terms are separated by plus and minus. So just looking at what's inside these parentheses here, I'd say there are 3 terms, okay? But they're being grouped together by these parentheses, and I'm supposed to subtract this whole thing. The parentheses are acting as sort of a container to turn these 3 things into one thing, and I want to subtract the whole thing, which means I need to subtract 3/5 x squared, okay, so minus 3/5 x squared. I need to subtract negative 4x, which means add 4x. And I need to subtract negative 1/6, which is to add 1/6. So this is what I'm asked to do. Okay? Now I'm looking for similar terms. Similar terms can be combined. Now what are similar terms? They have the same variables raised to the same powers. So for example, I see a 9x squared here and a negative 3/5 x squared there. Now the numbers out front are different, but the x squared part, that's the same variable x being raised to the same power 2. Those are similar terms. So what I want to do is I have 9 of these things I call x squareds, from which I subtract 3/5 of those same things. Okay, so I've got 9 minus 3/5 x squared. We'll worry about what that is in just a second. Okay, do I see any other similar terms? Well, yes, I see 3/2 x here and a 4x over there. Those have the same variable x raised to the same power 1. So those can be combined. I have 3/2 x plus 4x. So in the end, I have 3/2 plus 4x. And there are also similar terms here at the end, the constant of 2/5 and the constant of 1/6. Those have the same variable part. That is to say, no variable at all. Okay, so I want to add, these parentheses aren't important, but 2/5 plus 1/6, just to show the thinking process. I want to combine those. Now it's about adding fractions, which we know requires common denominators. Okay, so I need to write 9 with a denominator of 5. Well, 9 times 5 would be 45. So 45 divided by 5 is 9, from which I need to subtract 3/5. Okay? Over here, we've got 3/2. I want to add 4, but I need a denominator of 2. So how do you write 4 with a denominator of 2? Well, 4 is 8 divided by 2, so that would be 8/2. And now I need a common denominator here. This is maybe a little bit trickier. thinking through what are the multiples of 5 and what are the multiples of 6 and what's the smallest number that's a multiple of both. The answer is 30. Okay, so looking at 5 and 6, my LCD is going to be 30. That's the smallest number that's both a multiple of 5 and 6. Now I can turn 2/5 into a fraction where the denominator is 30 by multiplying the top and the bottom both by 6. Okay? If I multiply 6 over 6 by 2/5, I get 12 over 30. And if I multiply, let's see, to turn this denominator into 30, I would need to multiply the 6 by a 5. And I have to also multiply the top by a 5. Okay, so that nothing really changes. That gives me 5 over 30. Now I'm ready to go ahead and combine these numbers. So 45/5 minus 3/5, that gives me 42/5. 3/2 plus 8/2 gives me 11/2. And 12/30 plus 5/30 gives me 17/30. And that would be my final answer. Okay. Okay, here's another example. Again, I'm just trying to combine similar terms. I've got 4 times x squared plus 3 minus 3 radical x plus 1 minus the sum of the square root of x plus 1 and 3 x squared plus 3. And again, as in the last example, the first thing I'm going to do is I want to subtract everything inside these parentheses. So I want to subtract the square root of x plus 1, and I also want to subtract 3x squared plus 3, so minus 3x squared plus 3. Now that we've distributed that negative sign, this is what we're looking at. And again, I'm looking for similar terms. Okay? I'm going to bend that definition of what I said similar terms were to encompass a little bit, be a little more general. Okay? So I've got 4x squared plus 3's over here, and I've got minus 3x squared plus 3's over there. Okay, now without knowing what x is, I don't know what this number is, but this number here, x squared plus 3, is the same as this number here, x squared plus 3. Okay? And if I've got 4 of them over here and minus 3 of them over there, those can be combined. Okay, if I've got 4 over here and negative 3 over there, combine them, you have 1. Okay, you have a single x squared plus 3. 4 minus 3 is 1. There's a 1 out front that I don't really need to write. Okay? Now, I see the square root of x plus 1 here and the square root of x plus 1 here. I've got minus 3 of them and then minus another one of them. Okay, so that's minus 3 of these things minus another one of those things. That's minus 4. That's minus 4 square roots of x plus 1. And that's it. Speaking of combining similar terms, we can also combine radical expressions in a way. So here you've got, these are radical expressions, of course, because we see radical symbols. We've got radical 72 plus radical 50, or the square root of 72 plus the square root of 50. And I don't know what those numbers are. These are not perfect squares, so taking their square roots would be a little bit ugly. But let me see what I can do. There's an interesting property about radicals, or square roots, that follows from properties of exponents. So you'll see over here, here's the property of exponents that's fairly obvious. If I have a product being raised to a power, I want to raise each of those factors to that power. Now if you write it in radical notation, this is what it looks like. And it says that the square root of the product is the product of the square roots. It turns out to be helpful, especially here. It means that I can take the square root of 72 and I can rewrite it to be the square root of 36. Maybe I'll do it this way. I'll say that's the square root of 36 times 2. 36 times 2 is 72. And 50 is 25 times 2. Okay? Now, sure, 72 is also 9 times 8. 50 is also 10 times 5. Why did I choose to factor these numbers in this way? Well, I'm trying to write them as a perfect square times a number that's not a perfect square. And I'm trying to take that perfect square to be the biggest perfect square that these are multiples of. So 72 is a multiple of 9, and 9 is a perfect square. But like I said, 36 is bigger. 36 is the biggest perfect square that 72 is a multiple of. Similarly, 50 is a multiple of 25, which is a perfect square, and it's the biggest perfect square that 50 is a multiple of. Why is this helpful? Because of this property that I've got on the board over here. It says that I can take the square root of a product and write it as the product of a square root. Since some of these are perfect squares, let's see what this looks like. We've got the square root of 36 times the square root of 2 plus the square root of 25 times the square root of 2. And that would be 6 square roots of 2 plus 5 square roots of 2. Now, without knowing what the square root of 2 is numerically, it doesn't matter. I've got 6 of them here and 5 of them there, and I'm adding them together. 6 plus 5 is 11, so this would be 11 radical 2. Okay? Okay, so we know how to add and subtract algebraic expressions by combining similar terms. But what if I want to multiply algebraic expressions together? Specifically, what if I want to multiply an algebraic expression here by an algebraic expression here, where one of them is actually a sum? Okay? The parentheses tell me to treat that sum as one thing, so I am multiplying this times that. But how do I do that when that is actually a sum of several things? Well, the way that multiplication is interacting with this addition is handled by the distributive property, and it tells us to distribute the a to both of these terms so that I get a times x plus a times y. That's called the distributive property. That's how it looks in this case. If you have two terms here being multiplied by two terms here, then you are actually going to have four products. 2 times 2 is 4. So there's a little acronym to help us remember this. I multiply the first term by the first term, and I get ax. I multiply the outer terms together, the a and the y are on the outside. The outer terms gives me ay. I multiply the inner terms, the b and the x are on the inside. I get bx, and I multiply the last term here by the last term here. That gives me by. FOIL is the acronym to help me remember first, outer, inner, last. But that only works when there are two terms being multiplied by an expression with two terms. In general, you should understand how the distributive property works more generally. And here's a cute example. If I want to multiply 26 by 157, it's a mental math trick to break those numbers up into sums so that I'm actually multiplying together two sums. And how does multiplication interact with addition? By the distributive property. What does it look like here? Well, one way to visualize this, or to intuitively understand what's going on, 26 times 157 is the area of this rectangle whose dimensions are 26 and 157. By breaking those numbers up and putting some markings along this rectangle, I can see, okay, maybe this distance is 20, this distance is 6, this distance is 150 and 7. What I want to know is what is the area of this entire rectangle, and of course it is the sum of the areas of these tinier rectangles that comprise it. So let's see. The area of this first rectangle is 2,000 because it's 20 by 100. The area of this rectangle here is 300 because it's 6 by 50. And this is acting like a multiplication table. I just fill out these numbers, and what I want to do now is add them together. I'm going to get 4,082, and that actually is the answer. I don't recommend drawing this rectangle every time you need to do it. Just understand that what's going on is that this 20 is being multiplied by the 100, the 50, and the 7. So it's being distributed. That's where these products are coming from, as well as the 6 is being distributed to all of these terms. So there are 6 products, and I can see them right here, or I can draw this rectangle and see them that way. Now what I really want to do is I want to multiply algebraic expressions where there are variables. So let's look at this. I've got 3x minus 5 times 2x squared minus 10x plus 7. Since there are 2 terms here and 3 terms here, 2 times 3 is 6. There are going to be 6 products. The first one is 3x minus 2x squared, which gives me 6x cubed. The next one is 3x times negative 10x. That'll give me negative 30x squared. Notice that I'm treating that subtraction sign as being part of the coefficient negative 10. 3 times negative 10 gives me negative 30. 3x times 7 gives me 21x. Now the 3x has been distributed to all of the terms on the right. minus 5 times 2x gives me negative 10x squared. Minus 5 times negative 10x gives me positive 50x. And negative 5 times positive 7 gives me minus 35. So those are my 6 products, and the only thing left to do is combine similar terms. I have 6x cubed, and I have a couple x squared terms that I can combine. Negative 30, negative 10, that gives me minus 40x squared. I see a couple x terms. There's 21x plus 50x, that's 71x. And there's just a constant of negative 35, only 1 at the end. So this is my final answer after combining similar terms. Let's take a look at this one. It's not much different, but now there are 3 expressions being multiplied together. And multiplication is actually a binary operation, meaning you can really only multiply 2 things together at once. So with these 3 objects, I have to choose what 2 do I want to multiply first. I'll just work my way from left to right. I'll multiply 3 times 2x minus 5. That's a simple distribution, and I get 6x minus 15. That's the result of this multiplication. And now to handle the second multiplication, I still have to multiply that by 1 minus 4x squared. This is a case where I'm going to FOIL this out. I'm going to distribute the 6x to the 1. I get 6x. 6x times negative 4x squared gives me negative 24x cubed. The 6x has been exhausted. Negative 15 times 1 is negative 15. And negative 15 times negative 4x squared is positive 60x squared. So those are my 4 products. And I have to scan the list to see if there are any similar terms. In this case, there aren't any. There's only a single x cubed term, a single x squared term, a single x term, and a single constant. So there's really nothing that can be combined at this point. I'm done. And that's my final answer. Let's take a look at another example. It looks pretty straightforward. It looks like what I need to do is distribute this 8 to these 3 terms inside parentheses and distribute this negative 3 to these 3 terms inside parentheses. There's actually a quicker way. If we zoom out for a second, we can, instead of looking at this as having to distribute, if we zoom out, we can kind of see that there are similar terms. We have 8 of these objects that are 2x squared plus 5x minus 4, 8 of them, and then minus 3 of those same things, okay? The idea here is that you don't know what x is, but if I told you that x was 2, this would be a number, and you'd have 8 of those numbers, and then you'd be subtracting 3 of those numbers. So if you have 8 of these things minus 3 of those same things, 8 minus 3 is 5. The answer here is 5 of those things, 2x squared plus 5x minus 4. And now, instead of doing 2 distributions and combining similar terms, I can just do a single distribution and get my final answer right away of 10x squared plus 25x minus 20. And that's a little bit easier. Down here, there's something similar going on. This is a kind of tricky one, but the same idea applies. I have a 2x squared plus 5x minus 4 over here, and a 2x squared plus 5x minus 4 over here. Now, in the next lesson, we're going to talk about factoring. So we'll talk about factoring out this common factor. But I'd like to just look at it as combining similar terms. I have a certain number of 2x squared plus 5x minus 4s minus a certain number of 2x squared plus 5x minus 4s. So in the end, how many 2x squared plus 5x minus 4s do I have? Well, I have 3x minus 1 of them, minus 7 minus 2x of them. And I can distribute this negative sign, so that's really a minus 7 plus 2x, which I can combine with my 3x minus 1. This is just combining similar terms. 3x plus 2x gives me 5x. Negative 1 plus 2, did I do that right? What am I? Negative 1 minus 7 gives me minus 8, sorry. And that needs to get multiplied by 2x squared plus 5x minus 4. And now you can perform the distribution. So you're going to get 10x cubed plus 25x squared minus 20x minus 16x squared minus 40x plus 32. Okay, and when I combine my similar terms, I have 10x cubed. These are similar terms. They combine to be 9x squared. These are similar terms. They add up to negative 60x, and then a constant of 32. So that's a sort of slick way that you could handle this. Of course, you'd get the same answer if you did all of these 6 multiplications and all of these 6 multiplications, and then you combine your similar terms. You'd end up with the same exact answer. This is just another way to do it. Now, there are certain products that we encounter over and over again. Specifically, we have the sum of 2 things squared, or the difference of 2 things squared. And instead of performing the distribution every single time that we see that, let's just do it once very carefully, and then just remember those formulas that come from this so that we can apply them in the future very easily. What I mean by this is, like, here we've got a plus b squared, okay? Now that, of course, means a plus b times a plus b. That's what that exponent of 2 means. And if we perform the distribution, we'll find out that that gives us an a squared plus an ab plus another ab plus b squared. Okay, that's just foiling this out. And the 2 terms here are similar terms that combine to be 2ab. So we get a squared plus 2ab plus b squared. We can use that formula now. Over here we have a difference, a minus b squared, and it's very similar. You just have to replace b with negative b, and this is what you get. But let's just do it once very carefully. We have a minus b times a minus b. And so when we distribute, we get a squared minus ab minus another ab plus b squared. And once again, these middle terms are similar. They can be combined to give us negative 2ab. All right? This bottom one goes by the name a difference of squares. These are perfect squares. We have something squared, a difference squared, or a sum squared. This is a difference of squared because of what's on the right. It's a difference of perfect squares. How does this arise? Well, just by foiling this. We get a times a, that's a squared. Be careful with the signs here. You have a times negative b gives us negative ab. Positive b times positive a is positive ab. And then b and negative b multiplied together to be minus b squared. Now the middle terms combine to be 0. They go away, and you're left with just a squared minus b squared. Okay, how does this help? Well, suppose you have 2x plus 9 squared. Now we know we're not just going to square the 2x and square the 9. No, no, no. When you have a sum being squared, you do square the first term and square the last term, but you end up with 2 times the product of the first and last term. We just did that. We know this. We know this from before. So if I think of this as something plus something squared, which is exactly what it is, okay? The role of a is being played by 2x. The role of b is being played by 9. But the result is going to be a squared plus 2ab plus b squared. Okay? I know this. We've done it very carefully. So that is 2x squared plus 2 times 2x times 9 plus 9 squared. Now I just have to see what this results in. So that's 2x squared is 4x squared, plus this would be 2 times 9 is 36x plus 81. And that's it. Okay. For this one, this is a difference being squared. This is another perfect square. It's the difference squared. And we have a formula for this. It looks like a minus b squared is a squared minus 2ab plus b squared. Okay, this formula is very helpful. The role of a is being played by 3x squared. The role of b is being played by 1 over 3x squared. That's fine. We're going to get a squared. That's 3x squared squared minus 2a times b plus b squared. So plus this last term, 1 over 3x squared squared. Okay, what are we left with? Well, this is I am going to distribute the square here. This is a property of exponents that when you have a product being squared, you have to square everything inside parentheses. That's different from when you have a sum being squared. It is not quite so simple to just distribute that 2 when the operation inside parentheses is plus. But when the operation is multiplication, 3 times x squared, yeah, I just have to square the 3. That gives me a 9. I have to square the x squared. That gives me an x to the 4th. Moving on, I've got minus 2 times this product, and it just so happens that 3x squared times 1 over 3x squared gives you 1. So our middle term is just minus 2. And our last term, we square the top and we square the bottom of this fraction. I get a positive 1 over 9x to the 4th. That would be my final answer. In the bottom, it looks kind of complicated, and you might just dive right in and start distributing, start foiling. But if you zoom out for a second and you realize that here's the sum of one thing plus another thing, and here is a difference, and the things that we're subtracting this time are the same things that we were adding over here. So it's a minus b. You see, a is 5x squared y, b is 8xy cubed, and this is the same a and the same b. Well, the formula, which we trust because we've done it very carefully, the formula tells us that this is a squared minus b squared. So it should be the first thing, that whatever I called a was 5x squared y, that should be squared, minus b squared, b is 8xy cubed squared, okay? And so in my final answer, I'm just going to square those things, so I get 25, this is 25x to the 4th y squared, minus, I square the 8, I square the x, I square the y cubed, that's 64x squared y to the 6th. And that's my final answer. And finally, let's see how these special product formulas can be used when the expressions that we see involve radicals. Okay? So here I've got a perfect square. It's a sum being squared, so I know I'm going to use this formula right here. And what does it tell me? Well, I can use it as a guide. It says that a plus b squared is equal to a squared plus 2ab plus b squared. All right, well, let's just go through this. What is a? A is 3. What is b? B is the square root of 9 plus x. All right, so a squared should be 3 squared. A is 3. B is the square root of 9 plus x. So there's my 2ab plus b squared. That's the square root of 9 plus x squared. All right, so what are we left with? Well, we're left with 9 plus, that's a 6, square root of 9 plus x. And in the end, this is the square root of 9 plus x squared. Okay? Now you could think of that as 9 plus x to the 1/2 power. That's the square root. And then it's being squared. And we know from the properties of exponents that we multiply these and we get 1. So the answer is 9 plus x. But just intuitively, what is the square root of 9 plus x? Well, it's the thing that when you square it gives you 9 plus x. Okay? So that's my answer. It would be nice to combine the similar terms, the constant terms of 9 and 9, which give me 18. 18 plus x plus 6 radical 9 plus x. That's my final answer. And down here, well, we have the sum of 4 and the square root of 2x minus 1 being multiplied by the difference of 4 and the square root of 2x minus 1. So this is going to use that difference of squares formula over here, that a plus b times a minus b gives us a squared minus b squared. Okay? This is very helpful. This is saving us the time of performing all of this distribution. We're going to cut straight to the answer, and it's going to equal the first thing squared, which is 4 squared, minus the second thing squared. That's the square root of 2x minus 1 squared. Okay, so what are we left with? Well, 4 squared is 16, and then we're subtracting something. We're subtracting whatever this thing is. You could put parentheses here, it's not necessary, but we are subtracting something. What is that something that we're subtracting? Well, it's the square root of 2x minus 1 squared. That's 2x minus 1. The parentheses here are actually important. You have to remember that we're subtracting this thing. It looks like one thing when you have the radical sign and the exponent here. These things, the 2x minus 1 has been grouped together with these symbols. But now that we square the square root, those symbols are going to go away, but they still need to be treated like one object. You're subtracting this whole thing. We're subtracting this whole thing. So we're subtracting the 2x, and we're also subtracting the negative 1, which is to say that we're adding 1. So my final answer is going to be 17 minus 2x. That's my final answer.